Hi there. So just to start off, my name is Lauren Fern, and what I'm going to be doing is giving you guys brief lectures on each of the sections that we cover in this book for this class. My hope is that these sections, these recordings will help you guys in terms of understanding the material and actually getting to see some examples worked through. So, before I start the first section, I just want to let you know that number one, it's a really good idea for you to maybe skim the section prior to watching these videos. And then, so skim the section, then watch the videos and work through the examples with me, and then perhaps go through and read the section again, working through the examples. And doing that prior to doing any of your homework will probably be quite helpful for you. On the Wiley Plus website, though, there are many lectures and there are some videos that you can access as well to give you some more examples that are actually worked through on video. So anyhow, I hope you guys find these to be helpful, and let us get going. All right. So this first section is on functions and function notation. So what we're going to be doing in this first section is just introducing different ways that we can represent functions. Probably a fair amount of this is review for you, but it's still really good to see, and so that we all kind of start the class in the same place. Functions are one of the most important ideas discussed in mathematics, and they are really fun things to play around with. Loosely put, when we talk about a function, what we're doing is we're talking about a relationship between two quantities. And when we talk about the relationship, it's actually a dependence relationship. So what I'm going to do is take a really naive approach first with functions, just to kind of give you an idea, and then we'll formalize this. All right, so when we talk about functions, we tend not to draw boxes that are smoking, but we're going to pretend that this is a machine. And what this machine has, we have inputs and we have outputs. Okay? The inputs we can independently choose. The output will depend upon what we put in. So we're going to pretend that each of these machines has its own little rule associated. All right, so suppose I say, I like the number 9. I'm going to put 9 into my machine, and it's smoking because it's working really hard, and out comes the number 14. So I scratch my head and I say, what would happen if I put in 0? Well, the machine works, and out comes 5. So in my head, I have a pretty good idea as to what's going on, but I'm going to put in one more number. I'm going to put in -5, and the machine's working really hard, and out comes 0. There's a pattern with what's going in and what's coming out. Okay? Our pattern is the following. Whatever number I'm putting in, I'm adding 5. And that's what's coming out. So if I put in a general x, I claim that what comes out is that x plus 5. That's the rule for this machine. Okay? Now, I can have a lot of different machines. We can do one more. Suppose I have this other machine, and suppose I put in the number 1, and out comes 1. Okay, not much information given there. What if I put in the number -3 and the machine works, and so out comes 9? Okay, I'm going to do one more number. Maybe you see the pattern, but if you don't worry about it. Okay, you're not going to have to guess these sorts of things. But suppose I put in the number 7 and out comes 49. Okay? In general, what's happening is x is going to x squared. That's the rule for that machine. Okay? Now, practically speaking, we're not going to draw machines every time we want to talk about a function, but I think it's a nice way of looking at these sorts of things. Okay? What I want to stress to you is, depending upon the function, and we'll get more into this in the next chapter, you can independently choose what you put in, but what comes out is dependent upon what goes in. Okay? So your input we tend to think of as the independent variable, and the output we think of as the dependent variable. We call them variables because they can change. That's in contrast to, say, like the number 5, which is a constant. It never changes. Okay, so a formal definition of a function is as follows. And before I give you this definition, I need to express to you that I never actually ask you to formally give me a definition on any test or quiz. But mathematicians like to define every term that they use, just so that we know that we're all speaking the same language. Okay, so a function is a rule that assigns certain numbers. These numbers are the inputs that we just looked at, to a definite output. Okay? So there's a couple words in there that are important. The rule, well, each function has its own rule. The rule for this function was take your number and add 5. The rule for this function was take your number and square it. Okay? And what it does is it assigns certain numbers, your inputs, to a definite output. Well, what does the definite output mean? What that is saying is that each input goes to exactly one output. In other words, when I put the number 7 in here, it only goes to 49. It cannot go to another number, otherwise it is not a function. I'll get to that toward the end actually of this particular section. Okay? Now, in practice, we discuss functions a fair amount. For example, I think you'll grant me that the amount that, say, a worker makes is dependent upon the number of hours that he or she has worked. Okay? In that sense, the independent variable is the number of hours worked, and then the dependent variable is the amount of money that the person earns. Another example is that the distance one travels is a function of the amount of time that they have traveled. Again, the independent variable is the time, and the dependent variable is the distance. All right, now what we have is something called the rule of 4. It's nothing that is extremely formal, but what it really says is that there's 4 main ways that we describe functions, and that functions can be represented. And I'm just going to briefly show you an example or two of each of these 4 different ways that we can represent functions. You'll see each of these come up in the book throughout this whole course. Okay. Actually, before I write them down, I am going to add that each of these different ways has their advantages and disadvantages. And depending upon the situation, some are more useful than others. All right, so that was called the rule of 4. And the first way that functions can be represented is either in words or, in other words, some sort of verbal description. Okay? So, I actually stated a couple of examples, but I'm going to state them again. One example is that the distance that one travels is a function of the time you are traveling. Okay? Again, the time is our input or our independent variable, and the distance gone is the output or the dependent variable. Another example is, how about this? The age of Antarctic ice, and we'll give that in hundreds of years, is a function of the depth below the surface. And we can say the depth is in meters. Okay? And again, the independent variable is the depth. And once we've gone to a certain depth, then we can get to what the age of that ice is. Okay, so the age is dependent upon the depth below the surface. All right. Next, another way that we can display functions is by a table. And you will see that this book contains a lot of tables. So let me just take us through an example using a table. Let us suppose that this table represents the number of gallons of paint needed to paint a house with an area, we'll call that area A. So here's our table. We have area and we have number of gallons. Okay, this table is given. So we have 0 to 50, 500, 750, and then 1,000. Okay, well, one of the first things you might ask yourself is, which is our independent variable and which is our dependent variable? So let's go through and think about this. We have to ask ourselves, is the area of the house dependent upon the number of gallons of paint needed? Or is the number of gallons of paint needed dependent upon the area of the house? I claim that the area here is our independent variable. Once we know the area of the surface that we're going to be painting, we can then know how many gallons of paint we need. So essentially what this is saying is, for example, if our area is 250 and I realize that we don't have any units given, we'll say just square meters or square feet, we need 1 gallon of paint. If it's 500 square feet, we need 2 gallons, and etc., etc. Okay? So that's another example where we can actually display our function with a table. Now, a third way is by drawing a graph. Okay? Now, I'm assuming that you're all at least somewhat familiar with drawing graphs and our Cartesian coordinate system. Excuse me. Okay? Hopefully you recall that this is the x-axis, or our independent variable axis, and this is our y-axis, or our dependent variable. Okay, I didn't write x and y because actually this example I'm going to use t for time. So let me just draw this graph, and then I'll tell you the little story behind the graph. Suppose somebody drives from home traveling 60 miles per hour. Okay? What this graph shows formally is the distance in miles traveled after t hours. So, initially, we're at home. 1 hour later, we're 60 miles from home. 2 hours later, we're 120 miles from home. And again, we can keep on going. Okay? So again, the distance traveled is a function of the time that one has been traveling. Now, as you recall, when we talk about our graphs, we like to label our ordered pairs. Okay? All of these points here are called ordered pairs. They're called ordered pairs because the order in which we write the numbers matters. Okay? You guys have probably learned that it's x comma y. In other words, it's your independent variable comma, your dependent variable. So if I wanted to write each of these as ordered pairs, this guy would be 160, and this one would be 2 comma 120. All right. We will be doing a lot of graphing, which is fun. So our fourth way of describing functions is using a formula. I'm certain that you guys have seen this before, but before I can talk about formulas, what I need to do is discuss what we call function notation. Okay? So, to indicate that y is a function of x, we can write this in a couple of different ways. Okay? We can write this as y is a function of x. You may or may not remember from a previous math class, and this is something that I'll emphasize every time it's relevant, but in math, of means multiply, is means equals. So if we're going to translate this, y is, so equals, a function of x. Okay? So this gives us our ordered pair xy or x f of x. Something really important for me to point out is that y and f of x are the same thing. Okay? Now, when we're looking at a function this way, our x, again, is our independent variable, and our y is our dependent variable. Okay? So back to the two machines that we drew, you may or may not recall that the first machine took x to x plus 5. The way we would write that in function notation is we would say y is equal to x plus 5, or we can just say f of x is x plus 5. We're putting this value of x in, and out comes that value plus 5. Okay? the other function that we looked at with our machine was x went to x squared. So the way we would write that is f of x goes to x squared. So let's just take a few examples here, just so that you're familiar with how to plug various things into functions. This is just crucial, and it tends to be confusing to some folks. Before I erase this table, though, I would really like to show you this table and how it relates to the function notation, and then we can get rid of it. Okay? Now, notice here, we don't actually have a function written. Pretty soon we'll be able to write a function for this. We're not there yet. Okay? But I claim, given this table, I can ask you, hey, what is f of 250? What is f of 750? Okay? What I'm asking is this. Remember, we said that our independent variable is the area. That's why it's going in parentheses. Okay? So, in other words, when the area is 250 square feet, I want to know how many gallons of paint I need. I claim that's 1. Similarly, when the area is 750 square feet, my function value at that is 3. Okay? Now, when you're given a table, you are only given a certain number of values. For example, if I asked you, what is f of 100? Well, we don't have 100 as an input. So until we start being able to write functions based upon tables, at this point, we can say, well, we don't know the precise amount, but I think you'll all grant me that 100 is between 0 and 250. Therefore, we're going to need between 0 and 1 gallons of paint in order to cover that area. All right, so what I would like to do is, actually, before I even give you another formula, before I erase this graph, why don't we take these ordered pairs and write them in terms of the function? In other words, we can certainly do those two values. Okay, what is this saying? When I'm 1 hour from home, or, okay, 1 hour from home, how far am I? Well, I've gone 60 miles. Notice that the input is the x value for my ordered pair, and the output is my y value. And in a similar manner, the way we can illustrate this ordered pair in function notation is f of 2 is equal to 120. Cool. All right, so let's take a function and let's play with some values. So I'm just making up this function. There's nothing really nifty about it, other than I guess I really like the number 2. Okay? Now, you are going to be given functions a lot this semester and then be asked to compute, say, what is f of 7? What does it mean to compute f of 7? Essentially, what we're saying is 7 is the number we're putting into the machine. What is the machine going to spit out at us? Well, the way you can look at it literally here is, didn't I replace an x with a 7 on the left side of my equation? And remember, when you have an equality, whatever you do to one side, in order to keep equality, you need to do to the other side. So if I replace x with 7 on the left side, I have to replace x with 7 on the right side, and I get the number 17. Okay? So what if I asked you, what is f of negative 1? Well, now everywhere where we see an x in our function f, we're going to plug in negative 1. So you get negative 2 plus 3, which is 1. Okay? What if I wanted to find f of, oh, who really cares, negative 5? Now I replace x with -5, and I'm going to get -7. If I wanted to write each of these three function values as ordered pairs, I certainly could. Wouldn't this first ordered pair be written as 7, 17? Again, independent variable, dependent variable. This second ordered pair would be -1, 1. And then this third ordered pair would be -5, -7. All right, so that is a few examples. Let me go on and show you a couple more. But first, let me find the ones that I want to show you. Oh, cool. All right, so let's do this guy. Again, what I'm going to be doing is linking the graph with ordered pairs and our function notation. So the first example that I would like us to do is to fill in the missing values. Specifically, I'm going to say f of 0 is what, and f of what is 0. And now I'll give you the graph so we can answer that question. Okay, this graph is given to us, and what we need to do is fill in our question marks. So how are we going to go about doing this? Well, remember, this 0 is my input, and I'm looking for my output, okay? So if I was going to write this as an ordered pair so far, this would be 0 question mark. Okay, so let's fill in the question mark. Well, when our independent variable is 0, what is our function value? Ah, it's up at 40. So here, our question mark is 40. Okay? Now, what's written here is different. Now I'm asking what independent variable takes me to 0. Well, again, if I was going to write this as an ordered pair, this is how it would look. Notice now I have that my y value or my function value is 0. Well, that's right down here on our horizontal axis. So I go to my horizontal axis and I say, this is where it's 0. What's my independent variable? 2. So I have a 2 there. Okay. Next, let's do this example. I'm trying to do a bunch of examples because I think the more that you guys see me work through, the easier your homework will be. One hopes. Okay, so the next example that I would like to do is as follows. I'm going to draw a graph. Not a very good artist on the board, but I do the best I can. And first, let me explain. Well, first I'll draw it, and then I'll explain what everything means. And 10, 20, 30, 40, 50, 60, 70, 80. And we'll just stop there. So, here we go. So, at 55, we're up close to 30. Okay. Let me just go down a little bit. There we go. All right, now what this shows is the following. This axis here is our speed in miles per hour, and this axis is our fuel consumption in miles per gallon. So essentially, what we're showing is that the fuel consumption, in other words, the gas mileage you get, is dependent upon the speed. Okay? So what do we see? We see that as our speed is down here, we get about 20 miles per gallon. It's optimal right around here between 50 and 60, and then our fuel consumption doesn't do very well the faster we go. Okay? So, what if from this graph I asked how much gas is used on a, how about 300-mile trip at 40 miles per hour? We're just jumping right in here. Okay, well, let's look at this. When we're going 40 miles per hour, we need to know what our fuel consumption is. And again, this is a rough graph. I think we could say at 40 miles per hour, we get approximately, boy, I'd sure like to round it to 30, but okay, fine. We get about 30 miles per gallon. Let's be nice to ourselves for the first section. Okay, so that's how many miles per gallon we get. Well, if we're going 300 miles and we get 30 miles per gallon, how do we compute how many gallons we need? Well, we would just take 300 divided by 30, and so we would need about 10 gallons of gasoline. Okay, so one other question I will ask pertaining to this graph is, according to this graph, what is the most fuel efficient speed? Well, how do we know what the most fuel efficient speed is? We look at our graph and we say, well, where does it look like we get the maximum number of miles per gallon? Okay, right here seems to be the high point of my graph. I go down, and at least by my graph, it looks like approximately 52 miles per hour. If I had drawn it more accurately, we would actually get 55 miles per hour, but this is good for an estimation. All right, so just a couple more examples that I would like to do. Oh, this is a great example. Cool. All right, here we go. What we're going to do now is we're going to let f of t be the number of people in millions who own cell phones T years after 1990. And what I would like us to do is explain the meaning of a few statements. Okay? For example, what does f of 10 equal 100.3 mean in words? Okay? Whenever I express things in words, I like to start with my input. So, question is, what is this 10? Well, notice I plugged 10 in for t, and t is the number of years after 1990. So one way we could start saying it is 10 years after 1990. But from that, it's like, well, okay, how about in the year 2000? This is accurate for sure, but it's a little more precise to say in the year 2000. Well, what happens in the year 2000? Well, the function is the number of people in millions who own cell phones. Doesn't that say 100.3 million people own a cell phone? All right. Let's just do a couple more. What if I want to say f of a equals 20? And I understand having another variable in there is not very satisfying. But the way we could say this is as follows. A years after 1990, 20 million people own a cell phone. In a similar but different unsatisfying way to look at this, we could say, well, what does f of 20 equals b mean in words? Well, now notice this is going to be 20 years after 1990, aka in 2010, B million people own a cell phone. How thrilling, huh? Okay. So, let us do one more idea in this section, and this is a really important idea. How do you know if you have a function? Okay? Well, two quantities can be related, but it doesn't necessarily mean that they're related by what we call a function. Remember, what makes a function different from what we call a relation is that each input can only go to exactly one output. Okay? That is the key. Let me show you three different relations, and then we're going to talk about which is a function and which isn't, and then I'll relate it to how you can tell given a graph. Okay? So let's call this guy f. Let's pretend that my relation f takes 1 to 2, it takes 2 to 3, and it takes 3 to 4. It's pretty darn exciting. And now let's talk about g, and let's say this takes 1 to 2, 2 goes to 2, and how about 3 goes to 5? And last but not least, what if I have a relation h, and I'm going to say 1 goes to 2, how about 2 goes to 3, and 2 also goes to 4? Okay? I claim that 2 of these guys are functions, at least of what we see that's written, and 1 of them is not. Okay? So, again, the key thing is that each input goes to exactly one output. Well, in this first guy, 1 is only going to 2. We're good there. 2 is only going to 3. 3 is only going to 4. So, yes, he's a function. Each input is going to exactly one output. Okay? Let's look at G. Well, 1 is going to 2, 2 is going to 2, and 3 is going to 5. Again, is each input going to exactly one output? I claim yes. Okay, what looks a little different here? Notice this output is gotten to by more than one input. That's okay with a function. We'll learn about that soon enough. What that means is he's not a one-to-one function, but that's okay. Okay? So, it's okay that one of your dependent variables gets hit by more than one independent variable. So, I suppose, given what I said, that two of these are functions and one is a not, by process of elimination, we don't even have to look at this and be able to say, nope, he's not a function. But let's talk about why. 1 goes to 2, we're all cool. 2 goes to 3, we're still doing great. Oh no! 2 also went to 4. And I claim that this breaks the definition of being a function, because each input goes to exactly one output, and here this input went to more than one place. On a graph, how would you be able to tell? We have what's called our vertical line test. We're going to be playing with lots of graphs that look like this. He's called a parabola. Okay? I claim this is a graph of a function. Okay? How can you tell? Well, again, each input can go to exactly one output. So no matter what x value I plug in, it's only hitting the graph in one place. So how does that pertain to the vertical line test? What that says is you have a function if each vertical line drawn passes through at most one place on the graph. Okay, what do I mean by at most one place? Okay, I claim this is also the graph of a function. But for example, if I draw a vertical line here, notice it doesn't go through any place of my graph. That's okay. The point is it can only hit your graph once. This is not a function. Again, because I'm taking an input, and notice it hits more than one place on my graph. And therefore, he is not a function, because this x value is going to more than one y value. All right. Well, I think that finishes up section 1.1. So I hope you all found that to be helpful. Thanks.